And now we go from the long wavelength part of the spectrum to the short wavelength part of the spectrum. Larry Esposito will tell us about the Cassini ultraviolet imaging spectroscopy of the Saturn system.
Thank you. And while my slides are coming up, I just want to mention something on a personal note. My talk is about the scientific results from Cassini's UVIS, but what a pleasure it was to work with the UVIS team and the Cassini science team, the Project Science Group. And it's amazing that that very productive and pleasurable activity gave rise to a whole number of scientific results. And I'm going to just give you a few of those from our investigation, the ultraviolet imaging spectrograph, UVIS. So what was the UVIS design? I don't have a picture, but it was designed to be a broad-based instrument for discovery and investigation of all the parts of the Saturn system, the planet, the moons, the rings, the magnetosphere, and the solar-wind interaction. And it follows a long line of UV spectrometers that were built at LASP at the University of Colorado, going back to Mariner 5 and 6, and continuing with Messenger and Maven. And UVIS, the experiment, emphasizes broad spectral coverage and moderate spectral resolution. So it's a particular design where we're looking for the big issues. It has the capability of imaging in one dimension, becoming 2D when we scan the slit across our target to make a drift in the other dimension. Also, as Roger Yell mentioned earlier, it included solar and stellar occultations, and the cell contributed from the Max Planck Institute, which was intended to measure the atmospheric deuterium to hydrogen ratio from Lyman alpha. That never succeeded to measure that ratio, but it did measure Lyman alpha at a number of targets, including Titan. And I'm going to talk about the top 10 discoveries from UVIS. If I don't get through them all, you'll get the general idea. And the basic idea is the breadth of discovery, both general, and because the mission allowed us to follow up on our discoveries, to do in detail higher capability measurements. And the present is that UVIS team members, essentially with very little funding and their associates, continue data interpretation after the mission ended. And I'm going to show you at the end some slides from Helsinki just last week that the team put together. We presented papers on particle sizes in Saturn's rings and in Uranus rings, opaque expanses of the rings, places where the rings are dark, ring origin and confinement, particularly concerning Saturn's F ring, and also UV air glow on Titan, which we compare to the Earth. So occultation, that's about the present up until last week. The future is the cloud studies, the occultations, the techniques we developed at Saturn can be applied to the Uranus atmosphere and to rings in some future mission. So some of the studies we're doing are developing techniques and potentially modifying those for future missions. So here are the top 10 studies, discoveries. I'm not going to read them off, but just to say there are a couple of those that have to do with the moon Enceladus, some that have to do with Titan, some that have to do with Saturn's rings, some that have to do with Aurora, involving the magnetospheric interaction with Enceladus, and one on our list having to do with the dark polar hexagon of Saturn, potentially explained by precipitation of particles from Saturn's, charged particles from Saturn's magnetosphere. So I'm going to show you some pictures. So as we approached Saturn in the year 2004, we scanned across the whole system. We took our spectrometer slit, went back and forth, and then we produced this two-dimensional figure of that, where the colors show the brightness, and this is the color of atomic oxygen. There's oxygen at 1304 angstroms. And what you can see is there's a cloud of oxygen that's around Saturn. This is the planet in the center, and it has its peak right here at about 5 Saturnian radii. And so somewhere in the Saturn system, there's a source of atomic oxygen at that location, both sides probably forming a torus. Later, we discovered this was the volcano's erupting water from Enceladus, which is broken down by sunlight to produce atomic oxygen. And so Enceladus became a focus of the mission, and also UVIS. And we studied, there's a picture here, of course, this is from the camera, but we studied the plumes of Enceladus by occultations, both by stars and by the sun. And we were able to measure the composition, the source rate, and actually what the composition was known from spectroscopy of starlight, which was absorbed by water vapor, and the structure of the plumes, these big structures and the little jets in them. And we observed a total of 8 solar and stellar occultations. From this, we found out the Enceladus jets are spewing about 200 kilograms per second of water with no significant variations over the mission. Now, there were variations found in the plumes. Those are probably related to chunks of ice, grains that are lofted by the majority of the flow, which is molecular. We also, on our way to Saturn, had taken a close look at Europa on the Jupiter flyby, and we found the Europa atmosphere is dominated by atomic oxygen, but with low density, and it's inconsistent with the water plume activity like Enceladus, which is showing when we eventually got there. So if there are plumes of eruption on the moon Europa, they're pretty different from the ones that we saw at Enceladus, and we want to tune up for the missions that are on the way to Jupiter now to both find the similarities and differences if there are European plumes. Now, we looked at air glow at Titan. It's primarily caused by sunlight and photoelectrons naturally, but the weak night air glow is from magnetospheric particle impacts. And here's a picture over here of the moon Titan, where the limbs are brightened, but there's also a band of latitudinal emission of night air glow. We were able to retrieve through star occultations the profiles of aerosols, nitriles, and organics in Titan's atmosphere in a region that is above that measured by Sears, and of course that measured by the Huygens probe, and below that measured outside the system. So we got into parts of the atmosphere that otherwise would be ignored. And we're able to measure the profile of hazes from multiple stellar occultations. And so you see here, I just want to make a comment that even we who are on the mission didn't realize the power of the long Cassini mission, the times we would get multiple observations. We talked about getting a stellar occultation of Saturn's rings that was substantially better than the Voyager occultation, but we didn't think about what you could do with 100 occultations or 200 occultations. And you can see here all the measurements from the multiple stellar occultations. This allowed us to measure the haze in Titan atmosphere, not only its overall average profile, but the variability among that. So one of the great achievements, not just its flexibility and ability to respond to discoveries, but the pure volume of data, which allowed us to put together a big picture. And just to give you an example, this is data from 4 of our star occultations. We had over 170 occultations of Saturn's rings, and an undergraduate student, Zara Brown, now at Arizona, who was looking at some particular aspects of these 4 occultations compared one to another. And you can see all the detail that we're seeing, the detailed structure, all of it real and all of it changing from orbit to orbit. We saw some things that were unexpected, clumps in the rings, aggregations that came and went, that had multiple lives, maybe like cats. And so we called these kittens, and We gave them feline names, and here is one of the first we saw, where we're taking measuring the opacity of Saturn's F ring. That's in there. It's sort of a broad feature, but suddenly the rings become almost totally opaque, and that's one of these kittens in the rings. They were also discovered by the radio occultation, which doesn't see most of the rings. It just sees the biggest clumps in the rings, objects that are millimeters more across, and the real rings are made up of dust. So these kittens are all that the radio occultations could see. And we're able to compare with the images to look at particle sizes, which we measured from the diffraction. And in one of these cases, the picture that was taken at the same time by the camera showed a creation of dust. So the same time we saw dust-sized particles in our occultation, the cameras were seeing a collision of two of these kittens, which knocked off a bunch of dust. We estimated the age of Saturn's rings using CDA results and the mass of the rings. And I want to say that there's a simple answer to measure to the age of the rings where you divide these two numbers. You divide the flux, the pollution of the rings, the mass pollution of the rings by the flux, and that gives you the age. Both of those things, all three, were measured by Cassini, but the real physical situation isn't quite so simple that you can just divide those two. So the Cassini result, as Hunter says, shows the rings are young, and what we've been looking at are loopholes and error bars in this. And our analysis says the rings are young, 400 million years old, plus or minus a few billion, so that they still allow the possibility of an ancient ring, and we talk more about that. We have a model for how the rings are polluted. That gives us an age estimate. One of the problems with the standard estimate of the age of the rings that's in the paper by Kempf et al. Is they simply do a division. They assume things are constant with time, but if there are processes that clean the rings, for example, oxidation of the organics in the irradiated ice removes them, you can even establish a steady state of pollution in the rings, which means the current state of pollution measured by Cassini says nothing about the age. We made some beautiful pictures of aurora, and here's the aurora on Saturn, but there's also something else here, the auroral footprint of Enceladus, and we see time varying arcs. So some of these pictures using the imaging aspect, so we use the spectroscopy to measure the abundance of water molecules at Enceladus. We use the occultations to measure the structure and dynamics of the rings. We use the imaging to make pictures of Saturn, aurora, and Titan as well. And here you can see the spot, the auroral footprint. Here's another picture we created of the auroral region on Saturn. Some recent results. We've been able to compare the day glow and night glow at Titan. They look very similar, which is hard to understand since one comes from magnetospheric particle precipitation, the other comes from sunlight. We've been able to compare the Titan air glow with the Earth's air glow in some of the same regions. Naturally, both atmospheres are dominantly made up of nitrogen, so we see a lot of the similar structure in these. So some of the Saturn work is coming back for implications, some of the Titan findings for implications for the Earth. And we've done some models. So here, just again, Saturn's F ring. The broad F ring is created by a small core of larger clumps, these kittens in the rings, and over 110 of these little structures. We've modeled one of those, and in that case, we can say something about the origin of the rings. It might have originated from a small moon, originally on elliptical orbit, and then the combined effect of the moon Prometheus, its co-rotation and Lindblad resonance, push the particles together in collision, an alternative to the idea that diffusion will spread the rings. We've looked at eccentric rings of Saturn, And these have a lot of similarities to the Uranian ring. So now the studies that we're doing with Cassini data may directly imply both the payload and some of the operations possibilities for future Uranus orbiter probe. In my summary, give you a quick flip through this. We have lots of spectra, lots of pictures. We have lots of occultations. UVIS made key discoveries about Enceladus, Titan, Saturn, its magnetosphere and rings. Our more recent results, still analyzing these data and comparing them in some cases to Voyager data, can explain ring structures and dynamics, the origin and perseverance of Saturn's F ring, and compare Titan's airglow to the Earth. And as I mentioned, Cassini UVIS results have direct implication for the next Uranus mission. Thanks for your attention.
Thanks so much, Larry. Great talk. I was wondering a couple of things, and maybe I'm off here, but about the rings. I've always wondered, we talk about the rings, and you said something about the origin. So we're talking about the rings as if they formed exactly at the same time, all of them. Is there any indication that, you know, the system formed at different times?
Yes. So if you imagine the rings were the product of the shattering of a small moon of Saturn, it might have been several moons. And the B ring might be the most ancient ring established a long time ago. There's evidence that the C ring was created much earlier, and the A ring may be of an intermediate age. People say that at the edge of the rings, the particles are drifting outward, and as they do, they get far enough away from Saturn to actually coalesce, and so they're continuing new moons being formed and moons being destroyed in a dynamic environment, almost an ecology of rings at Saturn. And a lot of the details of this come from Cassini measurements in the camera and the occultations.
Can I ask a second one? So I was just wondering also, you mentioned the aurora, the Enceladus aurora. I wasn't aware of that, but can this tell us anything about the ocean, the other liquid water ocean on Enceladus, the same way that we've inferred something about the tilt on Ganymede?
So I don't know that it says anything about the oceans. It's not my field. My understanding is charged particles in the magnetosphere are deflected by Enceladus down the flux tube that connects to the planet, and they flow down there, and when they hit the planet, they make a light. So it says something about the interaction. Potentially that interaction could be related to the conductivity of the ocean, but I don't know about that.
Thanks.